So thanks everyone for joining this webinar. And today's topic is pretty interesting. It's the hot topic in the industry right now with generative AI. And a lot is being talked about how generative AI works and the chat GPTs of the world and the different tools coming in different modalities. But the curious question a lot of folks have is the LLM, which is large language models, which enable chat GPTs of the world. What happens underneath them, decoding them and understanding that under the hood for some time. And that's what we're going to do in today's session. Before we get started, just quick point on bigdatatrunk, the company which we are. We are a professional training services company doing for several technology as well as soft skills for several years, mostly B2B, but also doing for B2C for public as well. Today's topic is relevant to generative AI. We have tons of different trainings in that area, as is definitely the most happening space. So would love to have any questions or inputs which you'll have and other ones. We'll share these links. If you have individual interest, we have public trainings, but if you have it for your company or your company sponsors you some credit and these kind of things, you can join those. And we have recently introduced a subscription model, a 24/7 pass, which is a pretty reasonably priced, very, very reasonably priced. Instead of per course, it's a subscription which you can get for the whole $10 for the whole library. And we'll share that link as well. So happy to see people using that and kind of think we've drastically changed our model instead of going per class and so on and so forth. So with that said, we'll switch back to the topic. And today's topic, as I said, is LLM under the hoods. Aparna, who is one of our lead instructors on AI, and she's been doing several great webinars in the past as well. If you have not seen, check out the generative AI models and several other ones which we have done in the past. So with that, I would like to call upon Aparna to take over the floor. Thank you, Aparna.
Thanks a lot, Raj. Good evening, everybody, and welcome to the session. Let me share my screen. We can get started. Is the audio clear from my end, Raj?
Yeah, I can hear you loud and clear.
Thank you. Okay, all right. Once again, welcome everybody. Today is going to be our first, I would say, introductory session on large language models. We will try to get a little understanding of what are certain components that go into building a large language model, and also try and understand at a very basic level the essential working of a large language model. Okay, so let's get started. We'll begin initially, with a little discussion of NLP, because probably that is where the whole field has evolved. There were a lot of limitations to basic or traditional NLP, which kind of gave rise to this entire LLM revolution, which is powering all the Gen AI kind of capabilities that we are really comfortable and probably, almost cannot function with right now. I think it's almost impossible for any of us to go back to a pre-chat GPT kind of a time where we were forced to do everything or look for solutions either on Google or Stack Overflow, or do a search all by ourselves. So, the way generative AI has been shaping up over the past few years, and almost all of that development happened post 2017 or 18, when attention-based models, which then led to the rise of transformer-based architectures, came up. So there is this really close connection between how LLMs work and them being very, very dependent on these kind of neural network architectures to function. So we'll try to take a look at that when we try to understand how LLMs function. We'll just talk very briefly about a few applications of LLMs. Maybe, at least we will try to work through at least one case study given time. And also there are some extremely cool visualizations available out there from some really amazing developers put up on the internet. So we'll try to look at least one visualization of how or what is the kind of work that happens internally within a large language model. They're still kind of in their developmental stage, I would say. although their capabilities have increased quite drastically, we are noticing quite a lot of issues with LLMs right now. There are, I would say, further more interesting kind of technologies or solutions coming up to fix these issues. For example, I'm sure most of you would heard about RAG retrieval based augmentation, agentic frameworks, and I'd say the most recent flavor would be like moving on from LLMs to LMMs, large multimodal models, which is probably the current flavor as such. So yeah, we will just try to understand what that directional shift is. Before we get there though, I always feel it's like definitely very, very important to have a basic or minimum understanding of natural language processing, the way it was done in a more classical sense. What were certain limitations which people faced when they were working with some of the more older machine learning approaches towards natural language processing. Like most of us are aware, natural language, even for human beings, when we are trying to set out to actually learn language right from the time like we are really young, um, most of our learning actually happens through listening. That's probably a reason why everybody says the more you talk to babies, the faster they pick up on language. um, so and repetition, the more and more you say a word, probably they kind of start picking that up. There is also a lot of background or contextual knowledge that human beings pick up without being explicitly told, just based on how the sentence is constructed. Even if it was linking back to some very old discussion, or even if there are a lot of parts left out as part of the conversation, we still do make very good sense out of it. Now, to be able to teach that level of knowledge to a system is kind of pretty tough. Wasn't done all that well even till around 6 to 7 years back. NLP as an area has been there almost since the 1950s, just as a domain. In fact, some of you are like regulars from some of our other webinars as well. One of the series we've done on deep learning, where we typically mention Eliza, which is one of the earliest chatbots that was created, and that was, I would think, available probably from 1955 or 56 onwards. So that was like the very first dialogue based application, very similar to the current state of our chatbots that we have right now, but very, very limited in its scope and functionality. So this whole idea of wanting to create maybe chatbots or some sort of question answering based systems, or any sort of information retrieval based systems, the attempts are being made from quite a long time. Although handling natural language is pretty complicated in the first place, we are trying to create systems that understand natural language the way we do, and thereby make use of that knowledge to also be able to generate the kind of responses that humans are pretty good at. One thing to really keep in mind though is, at the end of the day, a system doesn't understand anything beyond numbers, whatever it is, English, French, whatever are the nuances of the language, the syntax, the grammar. We should figure out ways in which you could probably encode them or in some sort codify them, so that a system is able to make sense of all of that. But then ultimately it has to be in some numerical fashion. Very briefly, a couple of issues with NLP. Again, just this entire topic of NLP, strengths versus weaknesses, how it evolved, the most common tasks that we come across within NLP, that would, like, in a detailed fashion, that's probably a topic all by itself. But let's just very quickly try to get a sense of certain issues with the regular or traditional NLP. Now we have two statements there: fruit flies like a banana, time flies like an arrow. It's essentially the same word, flies, but then do they mean the exact same thing in both of those statements, or does the context kind of completely change the meaning of that term for us? Obviously, within the first case, it's fruit flies as in being part of, I would say, probably like a common noun, one class of insects that happen to like the fruit banana. Whereas in the second sense, when we use the word flies, it is being used mostly to suggest some kind of activity, probably like a verb based action. So for us, it is very, I'd say, no, maybe not too easy to certain times, but at least fairly easy for human beings to understand that this term has very, very, very different contextual meanings depending on which kind of statement it is showing up. Just pick a couple more examples. She ate the cake with the frosting. Sounds like a good idea. And when we look at the kind of relationship, maybe, when we kind of go ahead and try and analyze that entire sentence, try to zero in on the most important terms that is giving us some additional information there, cake and frosting. At least the kind of relationship that this particular sentence suggests is that, assuming y, frosting is y and cake is x, y is a part of x. Once you have figured out this rule though, would it be right in saying that, this could be a rule that you could probably generalize everywhere? Now I have another very similar example. She ate the cake with the fork. So if you are going with that previous rule of y being a part of x, is fork a part of cake? Definitely not. So, although almost the entire sentence looks the same in terms of structure, the very last term that comes up when you're trying to link it back to whichever term that it kind of goes with, frosting with cake or fork with cake, again, the kind of relationship that both of those terms have is very, very different based on exactly how the sentence has been constructed and in what sense it is being used. um, some other very common issues that we come across, with NLP, if we were to just think of those as problem areas as such, like we saw from the previous slide, this whole question of one, ambiguity. You don't know in which sense that word flies was being used. Sometimes there is a lot of subtlety involved where you do not exactly spell out things, but then the meaning kind of is easy for us to figure out, but might be really tough for a computer to understand. Another typical issue could be the whole issue of ambiguity, sarcasm, where again, the terms that we use, especially when we are being very sarcastic, the terms might look like they're very positive terms, but on the whole, when we kind of convey it usually conveys some sort of a negative connotation. So those were certain issues with NLP. One other aspect about how things were handled, again, we are talking about the pre-deep learning, pre-transformer kind of era. I would say probably till, the end of 2010, maybe like that 50-60 year period in between 1950 to 2010. There were quite a lot of developments that did happen though. So certain ways in which the words or, the entire set of tokens that make up your training corpus as such, the way they would be represented or converted into a form which your system can kind of make sense of, there were these various different techniques that were used. One of the simplest things was probably the bag of words mechanism. You would extract each and every single word from your sentence or, your overall document, make that like one whole bag. And then there were a lot of probability based techniques that would go with it in terms of figuring out how likely is it that these two words can probably come together. The way you would combine them also, for example, this sentence in between, the cat sat on the mat. Um, if I was to go with the bigram, when we say the n grams here, n is a number that we can modify. So if I were to go with the bigram or the 2 gram approach, the cat would be 1 bigram, cat sat would be another, sat on would be another. And then you would look for like the probability of, if we saw the terms the mat, what is most likely to either show up before it or after it. So there were these massive probability related calculations that would happen over, let us say, an entire dictionary consisting of some 1 million words. And ultimately, this entire text would be represented in some sort of a numerical fashion, which is also referred to as some sort of a vectorized representation. One other technique, again, slightly old school, would be the term frequency inverse document frequency. How often would you probably come across the term cat as part of your overall documents? How often would you see the word the, is, and people figured out, that the terms that show up very frequently, like is, and the, these do not really add too much value, whereas the terms that show up a little less frequently, that is, that their ratio of showing up is inverse to the number of terms that is actually present over the entire document, that would give them more higher value as such. So we typically, for example, in this sentence, we'd probably put in a lot more importance on the terms cat and mat in comparison to terms like on and the. Again, those were slightly older ways of doing it. I'll just quickly walk through one simple application. This is an application that has been around from a really long time. Initially with the more straightforward NLP techniques, some of the ones that we saw on the previous slide, the way it was done was still not ideal. We'll see why, in a couple of slides. For example, this user review. I bought a phone a few days ago. It's a nice phone. The screen was really cool. The quality was clear too. Although the battery life was not long, it's okay for me. If I were to ask you all to guess what sort of sentiment is probably being conveyed through this particular review, I'd say on the whole, it is typically a very positive review. And again, the way it was initially handled was making up a list of terms that would typically show up in a very positive sense. Let's say, words like nice, cool, awesome, wonderful, great. And then you would also have like another equivalent set of the more negative sort of terms or words that indicate negative kind of sentiment. So assuming we do have access to these kind of lexicons, it isn't too difficult, to build a program, let's say with Python, to break this up, pick out each word, and then kind of go ahead and do a count. How many of the positive terms do we notice versus how many of the negative terms? So that was maybe, the approach with which these sort of classifiers, sentiment analyzers, were initially built. But then you'll see, it kind of gets tough pretty soon. That exact same review, we are kind of building onto it, maybe, a little more. And this is another similar kind of a review where there is like a lot more information being conveyed. Now we have like two different phones. I bought a phone, my girlfriend bought another phone. uh, Voice on my phone was not clear, worse than my previous one. Camera was good though. She was happy with hers. She wanted good voice quality. Mine was a disappointment. So, if I ask you to choose like one single sentiment with respect to this entire review, it is extremely tough to do that. If you were to go with that individual count kind of an approach, there's like way too much information being conveyed here. Also, probably, the phone that the initial subject bought is actually suggesting a lot of negative sentiment. The other phone that they are talking about is actually suggesting positive sentiment. So as long as the document is really simple and straightforward, the previous technique that we talked about would have been very easy to go ahead and carry out. The minute there is some more ambiguity, the minute there is added complexity, those kind of techniques start failing very, very soon. Let's talk about some applications which were already out there, in spite of all those backdrops or, the disadvantages as such. There have already been some really good applications of NLP with the drawbacks though. One, again, we are talking about machine translation, but kind of, think back to, I'd say, at least 6 to 7 years initially when Google Translate would operate, the way or the kind of accuracy that you would get from Google Translate versus look at it now though, it is extremely good. If you look at the translation quality, basic speech recognition, again, devices like Alexa or Siri, from 6 7 years back, or right around the time that they were launched, some 10 to 12 years back, either acting as those personalized chatbots, the kind of chatbot assistants you get either in typed text form or in the voice form from websites. Lots of information retrieval to a basic extent in all the search engines that we are used to. Now, for example, you go on to WhatsApp and you start typing out a message, the kind of autocomplete or predictions that you get. Again, we are talking about quality probably 6 to 7 years back when it wasn't done all that well. We did have these applications out there, and a majority of the time they were handled through simple machine learning techniques or with the more advanced deep learning techniques. So beyond 2014, recurrent neural networks started being used heavily because they can overcome a lot of the limitations of the earlier approaches. And post 2017 or 18, we are noticing a lot of transformer based applications, that handle a lot of these NLP tasks. One final example to kind of convey, areas where that straightforward NLP approach doesn't work. There is this entire snippet given. Again, for us, I would say it's not that difficult. Diana says, "Thank you, Frank. I'm not going through the whole thing." Continues digging in her purse. Frank is making some faces at a baby and then says, "That's a good looking kid you got there, Miss Barrett." It's Dana, but then, here he uses the first name Barrett. Or if, you compare this with the actual question, how is Oscar, the baby, related to Dana? For us, once we go through that whole text, let's say once or maybe one second time, we can very quickly give this answer that it's her son that is being referred to. For a system that makes use of those very classic traditional NLP approaches, this would be almost like an impossible question to answer. To have to go through all of this, make sense who is connected to whom, what sorts of words are linked to which other words. um, Cute 9-month-old boy, and then kid you got there, like making those kind of connections for an NLP based system were very tough. This is where LLMs come to the rescue. A lot of those issues we have talked so far, it could be subtlety, it could be ambiguity, it could be handling much larger pieces of text where there is like a lot of complex interrelationships among the text. Being able to remember from previous context, knowing exactly which of those terms to probably give more weightage or more importance to. All this comes very naturally, or is done at a very extremely good level with respect to most of these LLMs. And although in terms of popularity, probably all of us are definitely very used to all these various variants of ChatGPT. Quite a lot of us who make use of Google Gemini, we have certain equivalent kind of software tools or applications, whether it is for code generation, or we have other really good these ChatGPT alternates, I would say, whether it is Claude or whether it is Perplexity. But essentially, almost all of them, the way they function, there are differences in the kind of models they use. There is a little difference in the amount of training data sizes that they have been trained with, the kind of essential architecture that goes into the systems. But at a very foundational level, almost all of them make use of large language models, and that's what we're going to understand next. The minute we even hear those terms large, let's kind of break it up into large and the language models and first address that term large itself. They are massive, whether it is in terms of the computational power that is required, in terms of the internal parameters that make up the system, also in terms of the amount of training data that they have been trained with or exposed to. So a lot of times, I would say these alternate opinions are also correct to a certain extent, but strictly speaking, when we say large, from a very technical standpoint, we are referring to the number of parameters that are involved in creating that system, or the number of parameters that that system is expected to learn as part of that overall process. And we'll look at those numbers in a little while. One other generalized fashion in which people look at large language models is they have been trained on very, very large corpuses or training data sets, which is also true to a certain extent. This is, you could actually look at this visual also in terms of scale. Now, I know maybe part of it is very difficult to read, but that's also because some of the earlier models that have been out there, if you compare them with some of the more recent models, the very first variant of GPT-1, I think this was released just around 2020, based on one of the more initial transformer architectures. You will see here it deals with 117 million parameters, which itself seems like a massive number. But you compare that with some of the more recent ones. If we just stick to OpenAI, let's say, the Chat GPT versions, just compare, 117 million with 175 billion. That's like massive uh, exponential kind of a jump in terms of the number of parameters these models are expected to learn. In fact, they have not even released the actual number of parameters involved with the latest version, like 4.0, 4.01, the more recent variants that have come out. One of the best models from Google, their large language model, PaLM-E, internally includes over 500 billion parameters, that need to be worked out by the model itself before it can do any of those seemingly simple tasks for us, like answering back question, creating, a nice story based on a prompt, writing some code for us, generating whatever kind of data that we ask it to. So this is where probably, the first idea of that large, really large comes in. One other way to kind of put it in perspective, their capability as well as, the internal computational complexity, they have like typically increased by 15,000 times. We're looking at multiplying it by the order of 15,000 in terms of how the models themselves have evolved. One other aspect that makes these LLMs very interesting, also very complex at the same time, the amount of data that they have been actually trained with. Even the most basic earliest variant of any of these large language models would have definitely been trained on petabytes of data. 1 petabyte consists of 1 million gigabytes of data. At least that gigabyte is something that we're all aware of when, let's say, we download an entire movie, maybe runs into 2 to 3 gigabytes probably. If you look at the amount of either, pieces of text or words that make up 1 gigabyte of data, text data, let's say, I scrape Wikipedia or crawl over the entire web and make a listing of all the tweets that have been put out ever since Twitter has been around, it will definitely run into some petabytes of data. And just look at that scale, 1 gigabyte has 170 to 200 million words. And all these models are working probably, on this kind of scale. These are some of the major areas where they're getting their data. It could be just scrolling through the web. It could be all the digital books that are available, entire corpus of Wikipedia, all these archived files that are available in terms of research data, a couple of these LLM models, and the number of tokens or these words that they will deal with. I think, a lot of times, a lot of these aspects of LLMs are even like very difficult to comprehend or visualize. Everything goes into billions very quickly. In terms of how they have developed also, we've been mentioning it was like late 17 to 18 where most of this work started. A majority of all this has been possible because of a 2017 paper released by Google. Attention is all you need. So those of you who are like, very interested in these areas, that was probably that path breaking moment as such. Attention based mechanisms released by Google in 2017, based of which transformer architectures were released in 2018. So you see, slowly the model sizes are getting really huge. We are getting better and better variants of whether it's, Chat GPT or whether it is Google Gemini. They're getting much more better. From GPT-4 onwards, now we have multimodal support. You can talk back or converse with the model. It can create images for you. It can understand speech. So, instead of being just limited to text generation, currently a lot of these models can also generate images for us, videos for us, audio for us. So we are now working in that multimodal space as such, and their capabilities have been increasing drastically over time. So what are certain key components that make up large language models? We'll try to keep it simple because, especially by the time we get to attention-based mechanisms, it gets extremely complex and would need a good understanding of basic deep learning or neural network architectures to really understand that thoroughly. But we'll try to do as much as is possible, but still keep it slightly general and appealing to a more common audience, not just technical folks. The very first aspect would be tokenization, where whatever is that massive, billions of amounts of text put together that we were referring to, the way it is broken up and then fed into these models. Very first step, you would need to break it down into much smaller units called as tokens. And these are like the initial building blocks. For example, if this is your entire text, random text that GPT will break, when you break it down into tokens, sometimes for us, for the sake of simplicity, we could think of it as individual words. A lot of times, for example, this word tokenization has been broken up into two tokens. Token is one and zation becomes another. So there is like also a lot of pulling out of the prefixes and suffixes that happens coming down to the root word. So tokenization by itself is one entire topic of various different techniques being available, which is like, the best way to go ahead and do it for which of those LLM models. This is probably the way most of those ChatGPT based architectures, which work based on the BERT model, would actually do that. If this is my text, demystifying tokenization, that itself is my text, the building block of AI. The demystifying is once again broken up into these three terms. You're pulling out the suffixes and all. And before it is fed into the system, there are some added tokens that are put in at the beginning, at the end, so that the system figures out this is where each sentence ends and the next sentence begins. And then they are converted into some sort of a numerical fashion. How that happens, we'll just look at that in a minute. So what looks like text to us needs to go through this entire process where it is converted into a where it is converted into this numerical vectorized fashion as such before it can be fed into the actual network itself. Again, in terms of types of tokenization, it could be that very basic one that we saw where you just break it up into words. It does definitely need to be broken up into subwords. Certain times, if you're talking about, let's say, LLM, the system would need to understand, these are like three different words and like an acronym that is making it up. So you might need character level tokenization as well. The next most important aspect would be in terms of how you would create those sort of vectorized numerical representations of the entire text that you're working with, which is referred to as embeddings. Okay, so let's look briefly at embeddings as such. That's a simple, straightforward definition of embedding. You take your text, we understand text, computers do not. So you will have to convert it into some sort of think of it as, like a one-dimensional matrix, a lot of numbers kind of string together. So for each word or sentence that we're dealing with, you have to somehow do this numerical representation. And the way you would do that will determine how your models are actually understanding that input data. The embeddings themselves are once again generated through the use of deep learning neural network architectures. But instead of, like focusing on the math and the architecture part of it, just at a more everyday level, exactly what would an embedding mean? For example, you have all these list of terms on the screen: banana, bicycle, cherry, house. So if we were asked to kind of, break them up into similar kind of sets of terms and accordingly understand, what sort of relationship exists among those terms, like a regular exercise if we were to do. Now, for example, let's say we have put in all of the play related elements over here. We have these, the cherry, banana, and the strawberry showing up over here, the house and castle showing up over here. And now if our question is, if this is how, let us say, again, I'm not going into the details, but if in some fashion we were able to create this sort of a graph or a map, and then our question now is, where do you think is like the most suitable position for the word apple to come up? So even as if we try to actually do it like a game kind of a thing, I would probably go with an approach where it is closest to some other words that suggest something similar. For example, this is all a category of fruits, and that is where this needs to show up. That would be probably the best location. So we are looking for a lot of additional meaning also. This term belongs to this particular category, similar to this, hence also dissimilar to this. That's the kind of contextual information we try to capture when we create these sort of embeddings. One further example, that tries to showcase it's not just the meaning of the word, it's also a lot of I'd say relationships it has with other similar words, or the kind of difference it shares with dissimilar words. Both of them go into actually creating these sort of embeddings. So for example, again, this word cow, probably the best location for that would be this, because a cow is to a calf the way a dog is to a puppy. That is one way of looking at it. Another is, if this axis is, let us say, capturing this younger, the kid variants, maybe around this axis we are trying to capture the more adult variants of the exact same term. So now we are trying to showcase two different sorts of relationships, the way that we have actually put them on this space. Excuse me. All right. This is more a more realistic way of actually looking at how embeddings look like. They are these massive numerical vector representations, and some of these smallest embeddings typically that a lot of these LLM models work with. For every term, it's a minimum 4096 dimensional matrix. So if you look at 1 2 3 4 5 6 7 here, the word cat would be represented by this sort of a structure, which will have roughly some 4000 kind of entries, where how does that word kind of on, if you have to imagine a highly dimensional space, what are all the various characteristics that you would want to capture about that one specific word through this kind of a numerical representation. So that is here we are trying to show it at a very low representation or low dimensionality. LLMs, though, do it at a very high dimensionality as such. This is probably easier for us to understand. So if I were to plot them in space, and again, a low dimensional space that we human beings can visualize and understand, we can definitely say terms like cat and kitten would fall very close to one another. And maybe, there would be a little space between cat and dog. Similarly, if there is this much distance between the terms man and woman, you could expect a similar amount of distance to show up between these terms king and queen as well. I'm just going to stop share here and just go to, yeah, okay, give me a minute, please. Going to go to ChatGPT here to show you how ChatGPT makes use of this entire concept that we have just discussed. Just give me a minute, please. So what I'm doing is I'm just going to go to ChatGPT and ask it what sort of, the previous version that we talked about, which is the tokenization, and then the current one, which is we were only talking about word embedding. In fact, again, it's a lot more complex. There is also a lot of sentence level embedding that needs to be done. So yeah, I'm just sharing the screen again. Right. Okay. So, this is ChatGPT generating that response for me right now. What I asked was, how do you generate word and sentence embeddings? And I gave in this prompt, how do we make cake? So using this example, tell me what your process is. Is my, the browser window ChatGPT showing up? Just want to make sure the sharing is coming out right.
Yeah, we can see the
Yeah,
chat
okay,
GPT.
all right. Thank you.
Okay.
So, like we said, at the first level, it is creating these word embeddings, converting each of those words into that numerical representation. There are a lot of techniques available, and this is where differences between all those, whether it's ChatGPT or Google's Gemini or maybe Claude from Anthropomorphic, how, each of them would be using a very different style, which again, they have their own strengths versus weaknesses. Once again, they are converted into these sentence embeddings. So now, how do we make cake? These are the individual level tokens. These are, to a certain extent, it is showing us, it's obviously not showing everything. It's saying, 768 dimensional vector. Most often they go for 4096. This is probably a much earlier variant where it's doing only 760 dimensions. For each word, once again, when they combine it, they also have to create this sentence level embedding. So that happens in one of the initial layers of the transformer architecture. Now, based on this numerical representation, it is also trying to understand what other sort of terms are very likely to show up. Let us say whenever we use the word cake, when we see the word make, what other sort of terms are probably very likely to come up. Based on that information, after it has gone through millions and millions of similar looking samples and finding a lot of relevant knowledge, that is how it is going to be generating its response one word by another. So, this is like the overall illustration, how first creating the tokens and then creating all these word embeddings, the sentence embeddings. Based on that, working through thousands of layers of the transformer architecture, finding or looking for semantic similarity, and then creating the kind of response. You want to go back to the slides again? So, internally, in terms of the working, there is massive amounts of work happening. Looks like really fast and simple and quick to us, but yeah, the we've seen the number of parameters, right? Billions of parameters being calculated while it is creating the large language model in the first instance. We are mostly using pre-trained models, hence we see the, the responses come out really quick. The most important aspect that actually makes all of this work, like we've been saying quite a few times now, is this whole attention-based mechanisms, which are made use of in the transformer architectures underlying almost all of the AI tools that we work with right now. I'll just go into maybe, one or two aspects of what transformers do and what that whole term attention itself means. Um, the architecture is pretty complex and I won't say difficult, but yeah, needs very good understanding of a lot of deep learning essentials to make sense. But the best advantage that you get with these transformer or attention-based mechanisms is that, like we've said, when you go through a piece of text, probably certain terms are more important. Another aspect is some of them are linked to a few terms that you see later on, or you have already come across in terms of context, which would be more important in terms of, let's say, answering a question kind of a thing. So being able to assign different weights to those different terms based on how relevant they are, calculating that amount of attention that you actually need to pay to each of those terms, that is what these transformer based mechanisms are doing for us. If you notice here, how are you each of those terms being actually encoded into that kind of an embedding, and then a different sort of weightage being attached. Maybe how and you probably need to be understood in some sort of a joint representation to be able to do that conversion or some sort of translation. So in terms of architecture, we have these encoders, decoders. The bulk of the capability comes from the attention mechanism. One other very important aspect is the positional encodings. Cat sat on the mat versus mat is on the cat, although that's wrong. But although it's the same words or tokens that make it up, in an NLP approach, it would be the exact same set of terms in both the sentences. With this kind of an approach, it is also seeing which one comes first, which one comes next, what is the relative relationship among both those terms. Hence, this term positional, is it before, is it after, how does it go, is it adding some value to the term, is it sort of implying some sort of question. All that additional information comes because these models are capable of doing that sort of positional encoding, right? So these are some of the technical strengths of the transformer architectures themselves. being able to capture or calculate multi-head attention, being able to do that encoding by also giving a lot of importance to individual positions of the terms itself. That whole ability to calculate which term probably needs to be paid more attention. Then a lot of neural network related stuff, like being able to do good layer normalizations and all that. This makes a lot of those capabilities of all these Gen AI based tools possible. A lot of times these models are also pre-trained on those massive data sets that we have talked about, and then fine-tune to whichever kind of task that we are trying to solve. Now, for example, if you work, let's say, in a healthcare industry, you could make use of a more generalized version of, let's say, ChatGPT or any of those large language models, which has been trained on very massive training data sets. So it understands, all those term relationships and everything, and then kind of fine tune it with some sort of a more proprietary or more specific kind of a data set, a much more smaller instance of it, so that it works better for the specific task that you are interested in. One other very important aspect would be transfer learning. You could make it learn on one kind of a task, but once it has learned, you could ask it to go ahead and apply that kind of knowledge to another task. This is the final aspect I'd be talking about, and I'll just probably take a couple of minutes for a very brief demo. So reinforcement learning with human feedback. A lot of times they do make a lot of mistakes. Maybe the current versions are better. Even with the current version, probably I'd say 15, 20 days back, there was this instance running around, one example that a lot of these Gen AI based tools, they weren't able to answer simple questions like how many R's do you notice in a strawberry. It was only able to give the answer 2 instead of the 3. So there are, again, hallucinations is one issue that we are noticing quite often, which is them giving out very confident answers, but essentially wrong answers. So instead of letting us know that they're not able to probably give us the kind of response we are interested in, they just end up giving some sort of a response. So over the years, the way their accuracies have been improved is by also including some sort of reinforcement learning, where actual human observers sit, look at the responses, and then flag it off as good or bad. That becomes further training for the models themselves in order to get better. So whether it is in terms of detecting toxic behavior, whether in terms of detecting very inaccurate kind of responses, there is some sort of human intervention also that goes in terms of fine tuning the models and making them better. So this is also a very essential aspect to getting them to do the kind of work that we are interested in. Okay. So I'm just going to again stop share and open up this link, and we'll see like an end-to-end visual of how LLMs function, and kind of stop with that for today. This is available out there on the internet. I can also like share the link in the chat as well if you'd all want to kind of play around with it a little later by yourself. Or you could also just search for LLM visualization, and this is one of the links that definitely shows up. I'm going to go back to my browser window once again and just run that. One good reason again, why all these areas are doing so well is this massive community support in terms of making it all open source, and a lot of these resources being made available for public use. Extremely good resources, in fact. All right. To go into the entire thing and work through, just this demo, we could actually walk through and talk through for probably a couple of hours. But this is one of the smallest architectures that you see towards the right, the Nano GPT, which is only having like, under 1 million parameters. Like we said, the most recent GPT versions have over 500 billion parameters. Now, if this is, your input here, I hope it is visible. It's a little small though. How to predict text. So if I have typed out how to predict and I stop there, what is like the most likely term that the system is going to predict for us, which is how a lot of these models work, word by word prediction, based on what it has already seen so far. The likelihood of coming up with the word text or the word tokens or the word words how does it know which word to actually come up with? So you have your input, which is, like we've discussed, first goes into some sort of an embedding. I'll just play maybe, a couple of stages of this. Again, those of you who are interested, you can do that in more detail. In fact, all these in-between layers involve huge amount of very complex math that goes into all these transformer layers. So first, your term has to be converted into this embedding that we notice on the right-hand side happening. And then at the next level, first, tokenize, create that embedding, also include some sort of positional embedding, which is what these three structures are trying to tell us, which takes quite a lot of work to get that correct. After having done that, they combined to give your overall input embeddings, those vectorized matrix kind of representations that are being generated. And then these are then fed into the next layer. And from here on, it's a transformer architecture that is calculating a lot of those attentions, doing a lot of layer normalizations. I'm going to go back. Okay, so we are here at this layer. Almost all of these here until the output layer is very complex deep learning architectures being worked out as part of these large language models, trying to understand, once I see these three terms from all millions of tokens that it is already aware of in terms of embeddings, which sort of embedding makes the most sense in order to suggest what kind of next best term would make sense here. Just quickly moving on to the output here once again, or go to the layer before the output and continue. Okay. So once again, it develops those kind of output embeddings, which are further once again created back into the kind of text that we can see and understand. So yeah, massive demo, this one. In fact, if you were to go through every single step, you could also try it out with some of these other variants. If you look at this number of parameters with GPT-2 versus GPT-3, and just look at the architecture itself, the number of transformer blocks that are involved into creating these models keeps getting very massive very, very quickly. In terms of the applications that are available out there, it could be question answering systems. We now notice, that they are capable of creating code, they're capable of creating audio. It could be any sort of information retrieval based systems. It could be any sort of question answering, chatbot kind of devices, where almost across the board, the internal working happens to be done through these kind of large language models. One other very interesting aspect is much smaller working variants of these models are also available, which you can plug in into whatever sort of application that you're trying to build. So if you're interested in getting, let's say, API level access to some of the ChatGPT or the Gemini models, it is not very tough to do that. The models themselves are trained and ready. You could plug them in into some other application that you are trying to make use of. So I'm just going to stop here. In fact, again, all the various variants of LLMs, their strengths versus weaknesses, a lot of these ethical bias kind of issues. This is like a massive topic to cover. So I think, I focused on just kind of showcasing what kind of work actually happens into building these kind of LLMs. So from my end, I'm going to stop here. So we have at least a few minutes left over for question and answers. And then we do have another upcoming webinar, where some of the more advanced topics in terms of what are issues that we notice with LLMs and how can they be fixed with the more newer kind of solutions coming up. We're going to be discussing that as part of some later webinars that are planned for the coming months. So thank you, everybody, and you can put in your questions in the chat. We'll try to answer.
Thank you very much for the wonderful session. Again, some of the feedbacks I was getting from the group, that visual is pretty cool. Totally agreed that people have put together such visuals on top of such things. And then talking about, right segue with Aparna mentioned, there is the next webinar which is coming up. Is going to take this step forward, exploring LLMs and RAGs. Is the next part in the series which we are trying to continuously build. We started with generative AI essentials, deep learning and several of the related topics, and we're continuing to build and go deeper and deeper. If you haven't got a chance to check those out, then feel free to go ahead and look at those recordings. This is going to take to our YouTube channel, the same place where we're going to post this recording. So I've posted those links in the chat, so you have access to that. We come through various meetup groups, not only this one, but we have Cloud and other ones. So I've given that link as well for you all to do. We have a lot of e-learnings, and one of the interesting ones, which I would say, which is completely free, is a ChatGPT introduction. A lot of people are using ChatGPT in a very basic way or a little sophisticated way, almost similar to an advanced Google, but truly not the best way to use it. I think this particular training not only gives you this little nitty-gritty of how behind the scenes happens, not the level of the LLMs, but generally how ChatGPT and the thought process, but also some advanced practical ways how really ChatGPT can be used, and you can make best of ChatGPT. So that's for free. If you would like to take subscription and take that free, or even try out the free trial, and then you can cancel at any point of time. So feel free to do that, and you will have access to several other whole series of things in the library that they have. A lot of practical applications, not only these sessions, but actually tutorials and hands-on on various topics. You have access to all of that. So feel free to do that. Aparna was mentioning about some of the advanced trainings coming up and taking this forward into a proper training. If you would be interested, that's another link which I've shared. So those links are available in the chat. So feel free to utilize that. If anybody has any questions, feel free to put in the chat. Aparna has thankfully put the form, a feedback form, which is a simple, very small, it should take a couple of minutes. We really appreciate if you all put a feedback and put us in the right direction. Our intent is to share to the community. Of course, we are a business, but at the same time, we want to share our 2 cents and our knowledge as a team. And there are a lot of great videos, which webinars we have done, but I think we would always love to get your feedback and course correct, improvise however best we can. So I appreciate if you can take a few moments to fill that and give us some feedback. I do see one question. I don't know if Aparna you see, but I'll read it for you. Did you mean to rag when you
Was it
you can plug
your applications to LLM? I don't know if there is some wordplay there, where you're trying to make it difficult for us to. Yeah, but I'm looking at it more from that technical meaning of the terms itself. RAGs are probably a more recent one, where once people have realized that there are quite a lot of limitations even to the LLMs themselves, that is they're trying to fix it through retrieval based augmentation. What my intent was, it is very easy for you. Let's say you go to Google Colab and then start building your own Python code. Maybe you have your own training data set of some very proprietary kind of in-house kind of data. So you could take a paid subscription to ChatGPT. In fact, Gemini allows it for free also to a certain extent in terms of experimentation. So you could get your secret API keys, and then instead of using ChatGPT as an external end user, you could make that a part of your application, where your application is kind of querying based on your own internal data set. Whatever kind of prompts or questions that you have will be passed back to the model along with certain additional parameters, and you'll be able to generate responses from within the code you build as well. So that was my intent behind that statement.
Okay. Yeah, I felt as well there was some wordplay there, but good attempt to do. And thank you. Several folks are putting some kind of words. Thank you. Great session. And the series is, yes, that's what our intent is, to build upon and continue to add more and more deeper to it. I think generative AI and LLMs are changing, evolving quite fast. And I think we're trying to, that's what we try to do, is keep up with that and share the 2 cents with the world. So thank you. If you have any questions, put in the chat. Otherwise, we are done for the session. Thank you, Aparna, again, for very detailed.
Can I just take a couple of seconds, Raj, if that is okay?
Yeah, I mean, you want me to pause the recording or continue the recording?
No, we can switch off the recording. Sneha had a question, in terms of what